Hello, everybody. Welcome to this second session on distributed cryptographic protocols. My name is Javier Herranz from Universitat Politècnica de Catalunya in Barcelona, in Spain. So it's afternoon here in Europe, and we are going to have two nice presentations in this session. Each of them will take approximately 20 minutes. And then after the two presentations, we will have 20 more minutes for questions and answers. So if you have any question, please go ahead, write your question, and I will forward your questions to the authors, and the author will be in live answering these comments or questions. Okay, so let's start with the first talk that will be given by Alexander Munch-Hansen, and the title of the paper is Stronger Notions and a More Efficient Construction of Threshold Ring Signatures. So, Alexander, it's your turn.
Hello, my name is Alexander Munch-Hansen, and I will be presenting Stronger Notions and a More Efficient Construction of Threshold Ring Signatures. This is joint work together with Claudio Orlandi and Sophia Yakoubov, both from Aarhus University, including me. So our contributions are primarily twofold. We provide the first threshold ring signatures of size O of t compared to O of n. Now, to help illustrate what a threshold ring signature is, as well as the various constructions within this paper, I will be bringing in my co-authors, Sophia and Claudio. So to begin with, if Sophia and we form this inner ring here, which will be of size t, we can then freely pick some outer ring of size n, such as this. Now, if we publish a threshold ring signature, this threshold ring signature will essentially state that t people from within this outer set of n people signed this ring, or signed this message. But crucially, it will also not leak the identity of us. So if the verifier, such as the third co-author Claudio here, takes this signature, he can verify that two people did in fact sign this from this ring, but he cannot tell who actually did it. He can simply say that t out of n people did it. Furthermore, this being a ring signature means that this inner ring, Sophia and I, can freely pick this outer set of size n. That's why it's crucial that we provide a signature size of size O of t rather than O of n, because now we can freely pick an as large set as we want to without having to suffer under the signature size growing as well. This means that we can safely gather a large set so we can stay more anonymous by hiding within more people. Furthermore, we provide new and improved security definitions to better capture realistic attackers. This essentially means that we can now guarantee anonymity even if there are insider corruptions within this inner set. So if Sophia is anonymous, is an adversary like this, she can still not leak my identity or figure out who I am. Perfect. That's because we consider this a more realistic setting where you cannot trust sort of anyone, really. So towards our construction, initially I will introduce digital signatures. So say you have me and I want to leak some information about some company or some evil organization or something. Now I provide this leaked information to a verifier, but how will the verifier know that the information came from me? Well, if I decide to sign this leaked information, the verifier can simply take my signature and my leaked information, as well as some information on me, and verify that this signature and the message is correct. But this is all well and dandy in the usual case. But now, since I leaked this information about some evil organization, I might suffer repercussions under it. Therefore, I would maybe like to stay anonymous and not specifically be this guy. So therefore, Rivest et al. Proposed something called the ring signatures. Now, if we take the same company and say it consists of these three people, then this forms a ring of these three people. Now, if we have this set of important investigators who someone provides this leaked information to, they will again need to know that it actually came from someone within the business. But providing a regular digital signature would again state that, say I did it, then this would again be very binding to me in a sense that someone would be able to take the information and guarantee that I was the leaker. Now, a ring signature instead simply says that someone within this ring of three people did it. So no one can come afterwards and blame me for leaking this information specifically. They will just know that someone within the company did it. So understanding this concept behind a ring signature, I'll now introduce threshold ring signatures, kind of in the same context. So a ring signature would say that it would be either one of these three. But what if it's not good enough that you simply have a single person stating it? What if the important investigators will need to know that several people actually agree on this information? Well, to achieve this, these three people within the company could find like everyone else working for the evil organization as well. And this would then form something called the outer ring, which is of size n, and the inner ring is of size t. So these three people then create this threshold ring signature that can be taken by the important investigators, and they can then verify that actually three people do all agree on this leaked information, so now they trust it more. But crucially, this threshold ring signature does not leak the identity of these signers. It simply says that T people within this entire evil organization all agree on this leaked information. So how do we actually build these threshold ring signatures? Well, why not just simply construct them from regular ring signatures? Well, if in that case, consider this scenario. You have a threshold of 2 and an outer ring simply of size n again. Now these two people could just publish 3 different ring signatures. Now a verifier is not capable of telling whether or not 2, 1 or even 3 people created these signatures, because they all must satisfy something called anonymity. The only thing the verifier can tell is that at least one person simply created 3 different signatures for the same information for the same ring. So crucially then in 2013, Ewan et al. Suggested a way of getting around this, apart from simply creating an expensive serial knowledge proof that would prove that each of these signatures were created by a different secret key, which would in turn also hurt the anonymity, as this would likely be interactive and it would allow all of the other signs to de-anonymize the others. So Ewan et al. Suggested using ring signatures but with an extra property to essentially do this. Now what they suggested was to use something called the linkable ring signature. But as far as we can tell, this linkable ring signature brings a different notion of linkability than what would be required to actually formalize a threshold ring signature out of it. I will get into how you fix this later. But essentially a linkable ring signature allows a verifier to take 2 different signatures and figure out if they were created by the same person. Now while it might fix this specific case here, it would essentially mean that given 2 threshold ring signatures, you could also tell like across the different signatures if the same person participated in the signing. This would break the anonymity. So how we decide to fix this is instead use something called unique ring signatures. Now a unique ring signatures are very similar to both linkable ring signatures and also ring signatures, as I suggested before. They were officially, or I guess originally, proposed by Franklin and Chang in 2012 and again in 2013. And it essentially just has some extra properties compared to ring signatures. Now one of them is again a notion of linkability. But whereas linkability would be able to link you across different messages and rings, if you used a linkable ring signature, unique ring signatures essentially satisfy that if one person creates 2 messages in 2 different signatures, but on different messages, they are no longer linkable. So the verifier cannot tell that these 2 messages were created by the same person. The extra properties that a unique ring signature must also satisfy is that of defamation freeness and uniqueness. Now anonymity and unforgeability are kind of obvious, but defamation freeness essentially states that you should not be able to create a signature that is linked to a signature of another party. So it is kind of unforgeability, but for the linking part of it. Uniqueness instead requires that T-1 corrupt adversaries should not be able to create T verifying and unlinked signatures. So this essentially means that even if you know some of the secret keys or some signatures, you cannot create a signature that both verifies and is unlinked to anything you previously know. So it essentially creates an idea of anonymity as well as unforgeability. Now, to introduce this unique ring signature construction, I need to introduce some of the tools that we'll need. First off, we'll need an accumulator, which will be depicted by this magic hat. Now, an accumulator essentially takes an entire set S of size O of n and is then able to squash this into a single value of constant size. Now, having access to this single value of constant size, someone can create a proof that they are within this set, and you can then give this value, this proof, and this squashed value only, and you can still verify that you were actually within the, I guess, pre-squashed set S, and this then returns accept or reject. So essentially, you never actually have to communicate this entire set S, you can simply communicate this value AS. Now, this accumulator must crucially be something called collision-free, essentially meaning that you cannot have two sets S and S prime. They are both squished to this same value. That would intuitively allow you to create a membership proof of simply being in the other set, and this would break it. Now, secondly, we also need a zero-knowledge proof. Specifically, we need a non-interactive zero-knowledge argument of knowledge. Now, a zero-knowledge proof essentially allows you to take some common reference string, some statement, and some witness, and you can create a proof, where this proof essentially shows that you know a witness satisfying this statement. Now, that means that you can simply take the statement and the proof, and then this will either accept or reject, based on if the proof actually holds or not. This zero-knowledge proof must satisfy zero-knowledge, soundness, and completeness, as well as simulation extractability. The only odd property here is simulation extractability, which essentially means that you can take a single proof and then you can actually extract the witness from this without any rewinding. This is usually done using some trapdoor. Finally, our accumulator is instantiated as an RSA accumulator, and this NISC is instantiated using something called commit and proof NISCs, or for short CP NISCs. This entails binding together several proofs by having each proof prove something regarding the same commitment. So you have some commitment that goes again in these different proofs. So knowing these tools, how do we actually instantiate unique ring signatures? Well, to begin with, these are 5 tuples, and the 5th one is on the next slide. So to begin with, in the setup phase, you set up the accumulator as well as the NISC. Now, to create a key, I simply sample some secret key, and I just compute my public key by lifting some global generator to the secret key. This generator is instantiated within the setup phase as well. Now this gives me a key pair. Then to sign a message, I take some message, I just sample a ring ad hoc consisting of these public keys, and then I just squish all of these public keys into a single accumulator value and create my proof of witness, or my proof of actually being within the set S. Now, having access to this, I can compute this value sigma prime. Sigma prime is essentially just a hash of the messages as well as all of the public keys within the ring lifted to my secret key. This is essentially what binds me to this message and this ring. Finally, the statement just consists of all of the values that we can leave public, and the witness consists of all of the values that we must hide, such as the public key and the witness of being inside of the set S, as both of these would leak my identity, and that would of course not be a ring signature then. We can then compute a proof of this being correct that proves that I am in the ring and that my sigma prime is correct. Now, publishing these values allows a verifier to just take the value, unpack it like this, compute the same accumulator value, and then verify that my proof is correct. After this, you just output accept or reject whether or not this NISC approves or not. Finally, we have the link algorithm. This algorithm essentially just takes 2 signatures like this. So say I publish 2 different messages and 2 different signatures. They will then be linkable if the same signer signed them, if the same message is used, and the same ring is used. And how would this be done? Well, the verifier essentially just checks for equality of these 2 sigma primes. This is intuitively holding, as these sigma primes consist of the message and the ring lifted to the secret key. So if the same signer signed them without knowing different secret keys, this will naturally give the same value. Finally, you just output linked to unlinked. Now, our construction essentially satisfies both deformation freeness and uniqueness, but I won't go into the proofs here. Both of these can be found in our paper. Finally, our threshold ring signature. So this is an actual 4-tuple, and it simply consists of a setup, keygen, sign, and verify algorithm. So in the setup phase, it's as simple as setting up this unique ring signature scheme. Keygen is again as simple as having a verifier or some party here generate your own key pair by calling your the unique ring signature scheme. Same goes for sign. In fact, if you just have a party or an inner ring consisting of these two people and an outer ring consisting of the rest, they have these public keys. Each party then simply calls the sign algorithm on the message in the set of public keys, as well as their own secret key, which gives back a signature for each of them. So having a threshold of 2, this will of course leave two partial signatures, sigma A and sigma S for Alex and Sophia, which can then be published. Now, a general assumption about threshold ring signatures is that you can simply just leave these signatures somewhere, because naturally, if you would give this signature to someone, this would also likely be because this is your signature, so this would leak your identity. So we just assume that we can sort of place these signatures somewhere, and then any third party can come and combine them. Now, this sigma dagger below combi sign is essentially stating that we also satisfy something called flexibility, which is a definition due to Okamoto et al. What it essentially means is that a new signer can just take this set of partials, the sigma, and then append his or her own signature, sigma, in this case sigma prime. Now, as long as this new third party is actually within the same signer set and wants to sign the same message, their partial will simply just mean that the threshold is now 3 rather than 2. Finally, for the verify algorithm, a verifier just takes the sigma, unpacks it like this into the two partials, and then verifies that each partial signature is correct. This then returns accept or reject. Finally, the verifier must check that each of the signatures are pairwise unlinked. If any of the signatures would be linked, that would mean that the same party created two different partial signatures, and that would of course mean that not T people participated in the threshold signature, and it is no longer a threshold signature. Finally, if all of them accept and all of them are unlinked, the verifier simply outputs accept. Now, these signatures are all of size O of t. That is because all of these partials that we create are of constant size, which means that this final signature, that is just the concatenation of all of the partials, will be of size O of t. And lastly, this construction satisfies anonymity and unforgeability. That is essentially just because all of these partials are unique ring signatures, so they satisfy anonymity and unforgeability, as well as uniqueness. We don't actually need defamation freeness, so that's why we do not care about this right here. So, because of each of them being anonymous, each of the partials leak no information about who the signer is, so they essentially leak no information about who you are within this outer ring. Because they are all unique, it means that a set of t minus 1, or in this case t signers, cannot create an extra unique ring signature. So if t minus 1, just me in this inner ring, I would not be able to create two signatures that both verify and are unlinked. So that means that our construction satisfies both anonymity and unforgeability because of that. Regarding further work, we would like to create an efficient relation for the non-interactive zero-knowledge argument of knowledge. Currently, since we use this commitment proof NISC, one of the zero-knowledge proofs that we need is just a general bullet proof currently. It would be nice to have a more efficient relation for this that would be specifically created for this purpose. Furthermore, it would be interesting to consider the plane model. Currently, we need the random oracle model for things such as the RSA accumulator. But the issue would be that if you move to the plane model, you would instead have to use something such as Merkle trees, which has witness proofs of logarithmic size. So that would break the constant size of each of the unique ring signatures. So finally, our contributions. We have strengthened security definitions to allow for insider corruptions. We have provided an asymptotically efficient unique ring signature scheme. Specifically, each of these signatures are of constant size. And finally, we have created a threshold ring signature scheme that is asymptotically more efficient than anything in prior literature, and it satisfies our new security definitions. Thank you.
Okay, thank you, Alexander, for this nice talk. So let's see later if there are questions for you. And now we move to the second talk of the session, which will be given by Anders Dalskov, and with an even longer title, which is Improved Threshold Signatures, Proactive Secret Sharing, and Input Certification from Linear Secret Sharing Isomorphisms. So please, Anders, go ahead.
Hello, everyone, and thank you for joining this talk, presumably. My name is Anders Dalskov. I work at a company called Partitia. I was previously a PhD student at Aarhus University, and I'm going to be giving a talk about this paper of ours called Improved Threshold Signatures, Proactive Secret Sharing, and Input Certification from LSS Isomorphisms. So let's get into it. It's a bit of a mouthful. The core primitive that we work with in this paper is linear secret sharing schemes, or LSSs for short. So a TN linear secret sharing scheme allows the secret S, it says up here, to be split into n shares such that if you have T of these shares, they reveal no information about S. If you have T plus 1 shares, they uniquely determine S, and you can like load Hello, everyone, and thank you for joining this talk, presumably. My name is Anders Dalskov. I work at a company called Partitia. I was previously a PhD student at Aarhus University, and I'm going to be giving a talk about this paper of ours called Improved Threshold Signatures, Proactive Secret Sharing, and Input Certification from LSS Isomorphisms. So let's get into it. It's a bit of a mouthful. The core primitive that we work with in this paper is linear secret sharing schemes, or LSSs for short. So a TN linear secret sharing scheme allows the secret S, it says up here, to be split into n shares such that if you have T of these shares, they reveal no information about S. If you have T plus 1 shares, they uniquely determine S, and you can like locally add these shares to get like shares of a sum. So most of you have probably seen examples of such a scheme before, right? So for example, additive secret sharing, where it's like an additive secret sharing scheme, additive linear secret sharing scheme, I guess, is a n-1 secret sharing scheme, where the way it works is that you pick n-1 random values from some finite field, and then you sum these together, subtract it from the secret, and then that defines the last share. So, but I mean, any n-1 of these shares will reveal nothing about the secret. Or Chemie secret sharing scheme, where you pick a random degree T polynomial, and then you evaluate this in a bunch of points, and then you give a point to each of the parties, and you put the secret in the constant coefficient. Okay, so I mean, a linear secret sharing scheme should be nothing new, and it is nothing new. Okay. More precisely, what we work with here is this idea, this trick, if you will, of putting your shares in the exponent. So the best way to illustrate what I mean by this is to look at a classical example, which is verifiable secret sharing a la Feldman from '87, I believe. And the way this works is as follows. So you give a Chemie secret sharing to each of the parties. So remember, this is the point of some random degree T polynomial. So the polynomial defined by these random coefficients here. But in addition to giving the share to each party, you also broadcast like basically this is the secret sharing polynomial, but like in the exponent, right? So you multiply all the coefficients of the polynomial onto some fixed group generator, G in this case. And now each party can like locally check that they actually got the right shares, right? They can just evaluate basically this polynomial in the exponent in order to receive their share in the exponent. And the reason they can check, of course, with their own share is because they can just, put their own share in the exponent, right? And then they can check that this actually matches what they received. Okay, this is, of course, this trick, of course, has been used in many different places, not just for verifiable secret sharing, which, of course, again, it's one example, but it's not the only one for sure. Other typical examples is various kinds of threshold cryptosystems, so threshold RSA, threshold decryption. I think this is it's Kramer-Schuk, if I remember correctly. ECDSA, I think they do something similar in a classical paper on threshold DSA signatures, polynomial commitments, and so on. And all of them really share the same trick, if you will, which is if you have a secret sharing of something, then you can move it into the exponent by locally multiplying your share onto a group generator, basically. And that is what we try to formalize here, because despite showing up in a lot of places, there's been no real focused treatment on what it actually means to put something in the exponent. And it turned, maybe not surprisingly, it turns out that actually the idea of multiplying your share with something in order to move it into the exponent, it generalizes. And the treatment that we do here is very focused on how this is practically useful. And therefore we also demonstrate a bunch of applications for this formalization of ours. The way we formalize is through this idea of linear secret sharing isomorphisms. And very briefly, what this means is it's just a way of moving your secret sharing from one domain to a different domain. And that's more or less what happens when you put your share in the exponent. Then you're moving your secret sharing from one domain to a different one. The nice thing about our formalization is that we show that it very nicely generalizes to computing actually bilinear functions, where the inputs and output domains of these bilinear functions don't actually have to be the same before, right? So a classical bilinear function that you work with in MPC is, of course, multiplying secret share values, right? So that's a secret share. Multiplication is, of course, a bilinear function, right? You take two inputs, you get one output. And a classical MPC bilinear function is, of course, multiplying two secret shared inputs. But we show that this actually generalizes in a very nice and a very neat way. So now you can also do other kinds of bilinear maps. And as I mentioned, we get a bunch of applications. In particular, we show that this can be used for digital signatures, for efficient dynamic proactive secret sharing schemes, and for efficient input certification. The ones I will be going over here is the digital signatures and the input certification. Okay, so the definition of a linear secret sharing scheme that we work with in our paper is as follows, essentially. So a linear secret sharing scheme over some finite dimensional vector space, this V here, for n players will be defined by a matrix with coefficients, of course, in this vector space. And we say that the ith row of this matrix belongs to party I. And we use like a suitable notation for talking about the submatrices belonging to more than one party, of course. And a lot of secret sharing, or basically any practical secret sharing schemes, so in particular the additive secret sharing case, the Javier, also in the paper we have a replicated secret sharing. All of these work with this type of formalization. It's just a matter of picking this matrix in the right way. And it's usually not very complicated. I mean, if you want to do Javier secret sharing, then this matrix, I believe, looks like a Van der Monde matrix, for example. To secret share something under this formalization, if you will, what you do is that you pick a random vector. So it doesn't say here, but the vector should have the secret on the first position. And then you multiply this onto the matrix and you give the ith row to party I, right? So this multiplication of this vector here, it just gives you n values, right? And these n values, you just give each of the n values, you give that to a player. Okay. The notation we will use is, again, I guess not surprisingly, we'll put these brackets around the secret, or the secret and the randomness, in order to denote the shares, right? So this just means this is the vector of shares, this is the values that each of the party holds. Okay. Such a scheme, LSS scheme here is secure if, I mean, this is again going back to the initial one, it's secure if you only have like t or less of the rows of the result of this multiplication, then they're independent of S. In particular, if they're independent of S, then they reveal no information about S. And conversely, if you have more than t, or if you have t plus 1 or more of the shares, basically, then there is some reconstruction vector that you can multiply onto your shares, and this will recover S. Okay, so not surprising. All right, so let's get into these LSS isomorphisms. So if we have this vector space isomorphism, then basically you can move between shares from V to U just by applying it locally. And this is not surprising given the formalization of what a secret sharing scheme is. By just noting that if we apply it locally, right, then it just corresponds to applying it like on this matrix multiplication. And of course, you know, it's an isomorphism, it distributes very nicely. It might look like a homomorphism is sufficient, and in fact we thought so in a previous version of our paper. The issue with that is that I mean, you get some weird examples of like homomorphisms that are not really meaningful for this. And I guess in order to argue about this being secure, you probably do need it to be an isomorphism, since then you can very easily make an argument about the randomness in the target share being as good as the randomness in the original share. Or in the share in the input domain is the same as in the output domain. Okay, and the common example of like what kind of isomorphism you'd use here is of course scalar multiplication onto some fixed scalar. So like you have your input is some x in some finite field, the output is going to be x times some g. So this isomorphism will be of course parameterized by some group. And this is what we use when we do stuff in the exponent, basically. The nice thing about this formalization is that it allows us to very nicely present like a generalization in particular for bilinear maps. So I already mentioned that, you know, a classical bilinear map that you would use for MPC is of course multiplication of secret values. In that case, the U, the V, and the W will all be the same, maybe some finite field, for example. But it in fact works for like any vector spaces here. And the way it does that is basically by using the same trick as we do when we want to do just regular multiplication of secret values, which is this trick described by Donald Beaver in the paper called Circuit Re-randomization Techniques, I believe, something like this, from '92, or what is more colloquially called just Beaver triples. And very briefly, I mean, it works like this. So if we have actually already a bilinear triple like this, you have the application of alpha and beta secret shared, you have the alpha secret shared in the U domain, you have the beta secret shared in the V domain, then you can compute this linear application of like the functions here, the bilinear map and so on, and this will give you a secret sharing of the inputs, the U and V here, right? So it's the same trick. You mask your values, you open them, then you compute some linear combination of them, and then you get the result. And this is because it's a linear function. Everything is linear here that this works. You might think, oh, well, but how do I get this bilinear triple? But it's actually very easy, because all you need is a isomorphism from like a nice, you know, MPC-friendly domain, such as a finite field, to, for example, say U, V, or W. And for the cases of, or for the bilinear maps that are perhaps like practically interesting, of course, such isomorphisms exist, right? So that would be, for example, scalar multiplication. So this function here is, I mean, it's a scalar multiplication, but applying it in the above technique, like in the above way here, would allow us to compute scalar multiplications where both the scalar and the point is secret shared. Or we could also do it with bilinear pairings, right, where both the input points are secret shared, and the output that we're going to get is going to be the evaluation of like a bilinear pairing on the two secret shared inputs. And for, of course, I mean, for both the scalar multiplication and for the pairing, we very easily have like isomorphisms from some finite field, right, to the, like, what would be the U, V, or W, because they are, again, just scalar multiplications. Okay. So So what we have basically, what our formalization allows us to get is something like some way to do secret computations on secret shared data, but like in a lot more general way. Now we're not like really restricted to just doing it to doing MPC on finite field elements anymore. We can actually do it on scalars, we can do it on groups, we can do pairings and all kinds of things. And the way we kind of illustrate this is by doing showing how to compute these Pointcheval-Sanders signatures securely. Or when I say securely here, it means where you can have the secret shared key, or you can have the secret key be secret shared, and you can compute it on secret shared messages, and I mean you can even compute it on secret shared public key if that's what you will, and that's what you want. And you can compute it on secret shared signatures, and you can have the result be secret shared and of a verification, if you will, like all kinds of things. The reason for picking Pointcheval-Sanders signatures is because it's, I mean, it's nice enough to brag. There's no hash functions or anything that like kind of breaks the flow here. And it's fairly straightforward to using these tools that I just presented to compute these signatures, right? So in order to generate a key, we use some MPC protocol to generate random values in the G2 group, right? The second input group. I mean, again, if we don't know how to do this, I mean, this is just generating a random value, so we can do it based on, for example, a seed if that's what we want. And we need like random points here, but again, like this is like standard MPC protocols we just use. And this gives us the public key, right? So I mean, here is a bit more simple than the protocol. Here is just like for up to R messages. We use this LSS homomorphism, like it's a scalar multiplication onto this group, right, to obtain the public keys. Very simple, we just move them into the domain, it gives us secret shared public keys, and then we open these. I mean, again, if we want to have, for some reason, the public key be secret shared as well, then we just don't do this last step, right? And signing and verification is similarly like straightforward, I guess. For signing, for example, given a secret key and giving a bunch of secret shared messages, we first pick a random sigma 1 here. If we want to have this sigma 1 be secret shared, then we can use this one, but for G1. And I mean, if such a function doesn't exist, if we don't have a way to pick random secret shared random values in this group, I mean, what we do is that we just pick a secret shared random value in the field, and then we use a suitable LSS homomorphism to go into the group, right? It's not a problem. Then we multiply the y's and the m's. So I mean, the dot product here it's a dot product, but it can also just be a multiplication if we do just have one message, right? And then we compute the w here as this thing. And then we use this homomorphism, right? Remember, this is a public value, so it's just a local application of this homomorphism to obtain this guy. Okay, it's a scalar mul here, but like it's a normal application of the LSS homomorphism, of course. And then we can output the signature. Again, if this somehow had to be secret shared, then we would actually involve the scalar multiplication, the one I described earlier. Verification. Also straightforward, right? You have the input is the public key, you have your message, you have your signature, and you're going to output a secret shared value, which is carries information about whether or not the verification was correct. So it's going to be 1 in the target group if it was a good signature, and it's going to be random otherwise. Why it's going to be random, I'm going to show that. Okay, so. I mean, the first step's not so important. It's only for malformed signatures. We compute the pairing, right? This is a linear application. It's essentially an LSS homomorphism. First of all, to get the yes, it's an LSS homomorphism in order to get the alpha here. You compute locally the beta in a similar way, and then you perform a scalar multiplication between some random value here and the alpha over the beta. The reason for using this random value here is because if the signature doesn't check out, then we want it to be at least masked, and this perfectly masks it, right? Because the the scalar multiplication here will like hide the information carried by like these two if they're not the same, basically. Okay. And of course, I mean, this is going to be 1 if alpha and beta was equal, and it's going to be something random if that was not the case, because of this this row. Okay. And if we implement this, so we implemented this, or we implemented the local operations required for this, in order to see actually like how expensive is it to perform all of these isomorphisms and other kinds of things. And like, I mean, it's not surprising they're not very expensive, right? It's regular group operations. I mean, they're actually even faster than you would normally have, because since we're doing it on secret shared data, we can we don't have to have constant time implementations of, for example, scalar multiplication or repairing. Okay, we can use these signatures. So we use these signatures to get, as I mentioned, dynamic secret sharing, dynamic proactive secret sharing, and we also use it to get certified input. So I'm going to talk about the certified input. And what we get is a very efficient n-party input certification protocol, because again, we can just apply any MPC protocol to this. There's nothing special there, like nothing inherent in the MPC protocol that makes this not work. I mean, any MPC protocol over a finite field, of course, will work here. And that's what we do. So in a nutshell, input certification for MPC just guarantees that if the computation is successful, so if output is produced and everything, then all the inputs were certified by some authority. So in particular, it means that, or in particular, this means that it's not guaranteed that the inputs, I mean, if the computation doesn't succeed, then it doesn't tell you anything, basically. And we basically just use the signatures. It's pretty simple. So given inputs, your values here, some signatures in these values, you secret share, well, the signatures and the values. Everybody just verifies the signatures on a secret shared, like using the verify protocol, and then they check if this is correct or not. And since, I mean, we can do verification on secret shared data, this is not an issue. We compare this to another work that does it for n parties, but they do it for like particular MPC protocols, and we get something that is like way more efficient because of this simplicity, I guess. So, and that's my talk. Now I'm a kind of couple seconds over time, so that's it. So thank you very much.
Okay, thank you, Anders, for the talk. Sorry to everyone for the problems that we had at the beginning. And I think we can start with the questions and answers. Actually, we have one question from one of the authors to the other one. So it's a question by Anders Dalskov addressed to Alexander about the first of the talks. And the question is, any idea of the size of such a threshold ring signature in practice? So with practical parameters, etc., did you implement something, or do you have any estimation of the size of these groups and the total size of a threshold ring signature?
So the short answer is no. We haven't implemented it, but we have come up with a sort of way of instantiating this as a commitment proof scheme, where you will separate this into 3 proofs, and then you would individually prove that the public key is correct, that the secret key is correct, and that the signature is correct. And 2 of these are sort of relatively straightforward. You can prove that the signature is correct, and that you can prove that the secret key is correct. And these are just essentially 2, like these are very close to just proving like a knowledge of an exponent. But proving that the public key is correct is a different matter, because this is now knowledge of double exponent, where this sort of acts in a weird way. So you would have to do this as a bullet proof. So that would, at least that's the naive version of doing it, where you would simply create a bullet proof for a general proof, which would then, of course, scale logarithmically. So it's currently it's not that bad, but it's a bit large by having to be a bullet proof.
I see. But like this scale logarithmically doesn't affect the overall claim of constant size?
No, because it scales logarithmically in the size of the witness, right?
Ah, okay. All right, fair enough. Yeah, that's true. It's true, I guess. Okay.
So if you just loosely argue for it, it's still constant size, but it's a bit weird constant size.
Yeah, but I mean, you didn't make any calculation, say, like if you take, you know, these parameters for the RSA accumulator, these parameters for the Lissig proofs and so on, then you end up with a proof that is roughly 200 megabytes. Or
Unfortunately, no, we haven't done that. Not yet, anyway.
Okay. I mean, that could be a fun thing to see, right? That really that it doesn't scale with the total size. Like
yeah, that it would.
The
a little bit interesting.
Yeah.
Definitely.
Okay, I have also one question. So the key point for your result is that you're able to build the first unique, linkable, whatever ring signature scheme with constant size, using similar ideas as Dodis and others did in 2004 for the simple case of ring signatures. But it's true that many people in the area seem to either don't know or don't want to mention this result by Dodis and others, because when people talk about ring signatures, they talk, okay, let's improve this from square root to logarithmic or so. So this is a maybe philosophical or general question. What happens with this scheme, with these Dodis and other schemes? And now what happens with your scheme? Why there are some people that don't consider this to be a full ring signature scheme, or in your case, a real unique ring signature scheme? Is there any reason? Is it because there is some trusted entity that at the beginning must do something, or why?
So I think it's a mistake that I do not mention the scheme due to Dodis et al. In my presentation, and we do pay respect to that in the paper now, which we might not have done before. I don't think there's any particular reason. I think it's just the fact that they work by using accumulators, right? RSA accumulators. So it's not something that can be done without any trusted entity to begin with. So in that sense, I think most people try and build these kind of constructions using strictly like less dependencies, right? So you don't need a random oracle and stuff like that. And we chose to sort of ignore these dependencies, these assumptions, and try and see if we can do a T-size signature rather than try and go the other way and remove the assumptions.
Mm-hmm.
I think that's why, anyway, because it seems like most cases people refer to stuff like Monero and stuff like that, where you don't want any assumptions or any dependencies or anything. And in that case, you can't use a construction that requires a random oracle, of course.
Mm-hmm. Yeah.
So that's I think that's why, anyway.
Yeah. But when you say it's based on both DDH and RSA, does it mean that somebody has to create an RSA key, a product of two primes? And this guy knows something, this factorization that could allow him to break something, or not? Not really.
What do you mean?
So if I understood it well, with a diagonal reading of your paper, the construction, it's not detailed in the paper, it will be in the full version, but it seems that it uses both RSA and Diffie-Hellman kind of operations, right?
Yeah, our construction does, since it uses an RSA accumulator. So you need your keys to be primes and stuff like that to be able to accumulate them. And it uses Diffie-Hellman to actually create the signatures, since our signature is just the hash of the message and the ring lifted to a secret key.
Okay, but when they are accumulated modulo some RSA moduli big N, something like that, right? And somebody created this module.
Yes.
So, my question is, this person who knows the factorization of this module, does he have any information that could allow him to break some property of the ring signature scheme?
Yes. If you know this modulo, you could in theory compute a fake witness. So you're proving membership of things that are not actually part of the accumulated set. which would of course break stuff like unforgeability, because you could just claim to be in a set that you're not.
Okay, so in a real implementation of this, this could be done by some multi-party computation or ceremony or something like that, right?
Yeah. This would have to be set up before.
Maybe you could use then results by the other talk.
Maybe.
Okay, I think there are no more questions to Alexander. Thank you. And for Anders, I also have a couple of questions. Yeah, when I started reading also very fast the paper as it's in the proceedings, I read something like already in the abstract, like linear transformations between different secret sharing schemes, right? In the third line of the abstract, different linear transformations between different secret sharing schemes. So I thought, okay, you are changing from one secret sharing scheme to another, like from one threshold to another, or from one access structure to another. And then I realized that this is not the case, right? If you start with a threshold T, you will finish with the same threshold T in all the applications.
Yeah. So I mean, if you think about, so there's been like a couple of other previous like works that are like sort of related, right, to this that does, for example, this transformation from one threshold to another. Like for example, like any honest majority secret sharing scheme such as Shamir or what's it called, replicated secret sharing, you can actually like just locally you can transform that to like an additive secret sharing if you want. It's pretty easy. So ours goes like, I mean, if you want to do like a commutative diagram, I guess, then you can see that this goes like this, but like ours goes like this. So you can combine our techniques, if you will, with these other ones. So now what you can get, for example, if you think, so the paper, for example, I mentioned in the talk from 2005 by Kramer and Damgaard and Ishai, that one, for example. So you can use the techniques they describe in that paper, which is like transforming, for example, from a replicated secret or from a Shamir secret sharing to a replicated secret sharing scheme. And then you can use that in addition with this idea of like moving between different, well, basically, I guess, different groups essentially. So you can use, and we kind of use, I mean, for an efficient instantiation of some of the protocols we have, I mean, you would kind of be forced to use this because then you'd use these techniques for generating efficiently random shares, for example, if you have an honest majority protocol. And for that, you would be able, like, you'd need this idea of doing the share conversion that they do in that paper by using like PRGs. And then you generate something in a sharing in a field, and then you just go to the group, and then you get a random group element, for example.
Yeah. Okay, and then you simplify, and then you use later the case of Poincheval-Sanders signatures. You said in your talk, this is because there is no hash functions, nothing that stops the flow or something like that. You said, are there other signature schemes, I guess, that with this property, right? Like Kamenis, Lisanskaya, or maybe even Boneh, Boyen, or any other? Do you think that your results apply there as well, or?
Yeah, I mean, any like nicely, I guess you could call them like algebraic, very nicely algebraic looking signature scheme would of course work. I mean, you could use these techniques for ECDSA signatures also. The issue there is that, I mean, these techniques, or the application to signatures in particular, is only really interesting because you get to sign secret shared data. So that doesn't really work with ECDSA, for example, because the message you sign have to be hashed. So you cannot like do some computation, get the result, and then do a signature on this result. That doesn't really work. Or you cannot have like a signature and then on this thing and then keep computing on it, because it's a bit meaningless to make a computation on the hash of something. So that's why it's like we picked the signature scheme. But yeah, any other of the, I mean, there should be like a bunch of signature schemes that have this property should work. I believe they use a variant of the Kamenis-Lisanskaya signature in this input certification paper that we cite and that we compare against.
Okay. And what about lattice-based or post-quantum secure? Do you think that signature schemes therein, is there any chance that some of them don't use hash function to hash the message?
Oh, that's a good question. That I'm not so sure about. I mean, I'm not.
No, me neither. But
but that is a good question. That I don't know.
I think the very fast ones, those in the last round of the NIST competition, all of them employ hash functions, I guess. But maybe there are other, because there was in the 2010 and 11 there were also papers about these homomorphic signature schemes and network coding and blah blah blah. So there were a lot of lattice-based signature schemes that were kind of algebraically nice, as you mentioned. Yeah. So maybe this can be also instantiated with them.
But I don't actually know exactly how this the technique of ours would play with something like this in particular. I'm not so familiar with them. And I mean, the one thing that is like, at least in the applications we have, that is sort of implicit here is that you need an MPC protocol that works over a finite field.
Yeah.
Because I mean, that's basically the whole point, for example, for the pairings is that I mean, all the groups there in the pairing setting all have the same prime order, and you do your MPC protocol over this prime order, because then you can easily get like a group element in the target group and in the two input groups if that's what you want.
Yeah, with lattices, shares will be integers, so no finite field. So
exactly.
A different.
Yeah, exactly. And then it becomes a bit, I would assume it becomes a lot more messy, or maybe even not like really doesn't work or something. I mean, maybe it does, but yeah.
Okay, let me see, no more questions. So let me thank both of you again for your talks and your answers. And for the audience, that's the end of the session. And we have now 3-4 minutes if you want to have fast coffee before the invited talk by Dan Boneh. Oh, sorry, I have one more question. What about for Anders? What about verifiable secret sharing? How does verifiability fit into your framework?
I mean, the example I mentioned in the beginning of the talk is, I mean, it's I guess an application of this thing that we do. I mean, so of course, like what we're trying to, I guess you could say, formalize in this paper is this idea of putting things in the exponent, something people have been doing now for 30 years in MPC and in distributed secure protocols and so on. Like exactly how it fits in. I mean, our technique is like this thing that has been done like in a lot of like previous works. So I think like what we actually do is like we put sort of like a formal treatment to it, and like words on like what you can actually do with this. That it's not just like, oh, if you have a secret sharing over a finite field, then you get a secret sharing in the, I mean, exponent by doing this. I mean, you can do it as long as it actually satisfies this thing, as long as you have a homomorphism between your one secret sharing domain to another, basically. So, and that it's like, it's not just like this one trick that works with verifiable secret sharing or Shamir secret sharing. It works like with anything. So if you have like a nice signature scheme or encryption protocol that uses, say, pairings, for example, in the setup phase. So for example, for attribute-based encryption, which is typically something where the setup is typically can be quite involved, I guess. Then you can, for example, use these techniques we have to very easily build an MPC protocol that gives you a distributed attribute-based encryption system where the setup is just like straightforward, because you can just run the setup algorithm, but now in MPC without any additional cost, basically, or fancy setup or any like specialized protocol. You just take an MPC protocol and then you just do this small trick, like just basically multiply with a scalar at the right points. I guess I can mention like here in the end that the reason it works for the pairings is because if you break down a pairing computation, it is just scalar multiplications. So that was like the reason why it's like you can compute the pairing locally if the one of the inputs is not secret shared, because then it's just these applications of these homomorphisms, but on one of the groups, basically.
Yeah, perfect. Okay, so we had a last question, but it was also about the possibility of doing this with lattice-based signatures. So you already answered to it. So I think we can finish this session. Thank you to everybody again, and enjoy the rest of the conference.
Thank you.
Bye.
Thank you.
Hello, everyone. I'm very happy to introduce the last keynote speaker of the Latin Crypt conference. I would say that there is no need to introduce Dan Boneh to anybody working in cryptography. He's a reference in the area. But since we have in this conference many students that, or maybe it's for some people it's the first conference, I'm happy to share and all the amazing achievements of Professor Boneh. So Dr. Boneh is let me introduce him. He's a professor of computer science at Stanford University, where he heads the Applied Cryptography Group and co-directs the Computer Security Lab. His research focuses on applications of cryptography to computer security. His work includes cryptosystems with novel properties, web security, cryptography for blockchains, and cryptanalysis. And he's the author of 150 publications in the field and a recipient of the 2014 ACM Prize, the 2013 Gödel Prize, the RSA Award in Mathematics. And he was also elected in 2016 a member of the National Academy of Engineering. So I would like to add that I think for people working in cryptography, we know that when Dan Boneh works on, so he's known for not only the depth, but also the width of his expertise. So for somebody working there, we know that if Dan Boneh works on something, this is something interesting and worth to look at. And that also he is well known for his educational leadership. Like for if you're students and you're starting working on cryptography, you can find his courses on MOOC or Coursera, and he's a pioneer also in sharing knowledge and helps us to follow what's going on. So please, Dan, the floor is yours.
Wow, thank you so much, Carla. This is a wonderful introduction. So let me say, first of all, it's really wonderful to be speaking at Latin Crypt. Thank you so much for inviting me. It's a wonderful conference. I wish it could be live, and I wish I could be at Bogota at the conference. But hopefully, I can be in person next year or in one of the future years. So I'm looking forward to telling you about snarks and polynomial commitments. It's a really exciting area. Lots going on in this space. There's actually so much to cover that it was really challenging to decide what to cover in like the 50 minutes that I have. I don't think I'll be able to say everything that I want to say. It's a pretty lively and vibrant field. So what I'll do is I'll sort of give you a sample of what's happening in the space. I'll give you lots of references to read for further reading if you want to get into the space. We'll see. Let's get started. We'll see how far we get. And I hope I'll excite you enough to think about working in the space, and looking forward to seeing your work in this area. So let's get started. Let me just switch here, just 1 second. All right. So the first thing we're going to do is we're going to look at basically, zero knowledge arguments for NP. Before we dive into snarks, let's just zoom out a little bit and just remind ourselves what zero knowledge arguments for NP are. And the particular flavor I want to look at are the ones that are derived from arithmetic circuits. Okay, so let's fix some finite field. It'll be a prime finite field. So pick some prime P, and we have the normal field. Now we're going to look at arithmetic circuits over this field. So an arithmetic circuit basically defines a function that takes n inputs and outputs one output in the field. And here's just a simple example of an arithmetic circuit that computes, a function of 2 inputs and produces one output in the field. I'll use this absolute value of C to denote the number of gates, addition, multiplication gates in the circuit. And I'm going to assume generally the circuits have an upper bound on the number of gates in them. So, some polynomial bound, which I'll denote by B. Now, we're going to be focusing on argument systems. And so argument systems are only sound and secure against provers that are polynomial time. And so let me quickly remind you what an argument system is. So basically, both the prover and the verifier know what the circuit C is. The prover has a statement, which we call X, and the prover also has a witness, which we'll denote by W. The verifier, of course, only has the statement X, and they interact in a protocol. And what the prover is actually trying to convince the verifier here is that, for example, C of XW is equal to 0. Yeah, so the witness, the prover has a witness for the statement X that makes the circuit evaluate to 0. Yeah, that would be kind of what the proof system is trying to do. Now, again, just kind of to remind everybody of the properties that these proof systems have to satisfy. I'll do this very informally because I want to get into technical details. I don't want to spend all our time on definitions. But just to remind everyone, the system has to be complete, which means that if, in fact, the witness is correct, then the verifier will accept. The system also has to be sound, which means that for every efficient prover, so every polynomial time prover, if there is no witness that makes the statement correct, then in fact the verifier will accept with only negligible probability. It turns out that often soundness actually is not sufficient, and often we need a stronger property called the proof of knowledge. Not only do we require proof that the witness exists, we also need a way to extract the witness from an efficient prover if the verifier actually accepts the proof. Okay, so if we have an extractor, then we call this a proof of knowledge, or a POK for short. And finally, for a zero knowledge proof system, we need that what the verifier sees, basically all the messages and all the inputs and randomness that the verifier sees. Basically, that entire transcript reveals nothing about the witness. As you know, this is defined using a simulator, but I won't go into the definitions of that here. Now, generally speaking, there are two types of zero-knowledge arguments. Yeah, so one type is basically what we call public coin arguments, which is arguments where the verifier doesn't have any secrets. All the verifier is doing is just sending random queries to the prover, and the prover is reacting to those random queries. Yeah, so those are called public coin protocols. And again, I imagine many of you, if not most of you, know that public coin protocols can be transformed into a non-interactive argument using the Fiat-Shamir heuristic. Basically, the verifier's message is derived from a hash function applied to the transcript up until this point. Okay, so public coin protocols can be made non-interactive, and in fact, these public coin protocols actually can be made. It's kind of amazing that they can be made to have very, very short proofs, and in fact, even fast verification. And those are called Snarks, which is what we're going to focus on in this lecture. I do want to mention also that there are private coin protocols. So this is where the verifier does have secrets that it doesn't tell the prover. Yeah, so it chooses some random value, keeps the random value secret to itself, and then sends messages to the prover, and the prover responds. Typically, those correspond to interactive arguments, right? So here there needs to be an interactive protocol between the prover and the verifier. Because the verifier is keeping secrets, the Fiat-Shamir heuristic no longer applies. So we have to use an interactive protocol. And in fact, there's been a lot of work on efficient interactive zero-knowledge protocols. I just listed a couple here. These are based on vector oblivious linear evaluation. And also there are systems based on circuit garbling. Very interesting work on interactive zero-knowledge. Generally, interactive zero-knowledge as an entire, when you look at the overall system, it can be more efficient than these public coin protocols. But these public coin protocols have the benefit that they're non-interactive and that the verifier's work, at least, is very, very, very small. Now, for those of you who are familiar with zero knowledge, you might be wondering, well, wait a minute, public coin and private coin protocols are actually equivalent. In fact, there's a result due to Goldwasser and Sipser back in 1986 that says that a private coin protocol can, in fact, be turned into a public coin protocol. Yeah. But unfortunately, this result sort of only works in theory in the sense that the derived prover, so when you start from a private coin protocol and you convert it to a public coin protocol, the prover that you end up with has to be super polynomial, has to take super polynomial time if it's using the private coin protocol as a black box. In fact, there are results of Vadan and Rafael Paz that show lower bounds on the running time of the prover. So actually, these transformations from private coin to public coin are actually quite interesting. If you use the private coin protocol as a black box, again, the prover has to be inefficient. It's actually kind of an interesting problem of whether there are conversions that do not use the private coin protocol as a black box and still end up with an efficient public coin protocol. Yeah, so in theory, these are equivalent, but in practice, they're actually quite different. And so we're going to focus on public coin protocols that lead to non-interactive arguments. Although I did want to mention that these two families of zero-knowledge protocols have different applications. For example, the non-interactive arguments that result in very short proofs, what's called succinct zero-knowledge, short proofs that are easy to verify. Those are, in fact, mostly used when there are many, many verifiers in the system. This is typically what happens in a blockchain system where a server might post a proof to the blockchain, and then all the verifiers need to verify this proof. In this case, we can't use an interactive protocol because there are many, many verifiers. They all want to verify the same proof. You can't have the server individually interact with each verifier. So we have to use a non-interactive proof, and we want the verification to be as fast as possible because there are many verifiers verifying this proof. So when there are many verifiers, we would be using we sort of have to use a non-interactive system. When there's a single verifier, it's perfectly fine to use an interactive zero-knowledge system. And a good example of a single verifier scenario is like something like a compliance auditor. And my favorite example of that, there's a single compliance auditor that you're proving a statement to, that you did something correctly. My favorite example of this is what we call zero-knowledge taxes, where if all your transactions are recorded on a blockchain, you can actually prove to the tax authority in zero knowledge that you paid the right amount of taxes without revealing anything about your financial state. Yeah. So in this case, it's fine to use an interactive protocol because you're only proving the statement once to the tax authority. So, you could have an interactive protocol with them. At the end of the protocol, they're convinced that you paid the right amount of taxes, but they know nothing about your finances. So this is kind of a cute application of zero knowledge. Maybe one day we'll actually get there when all transactions actually are recorded on perhaps in some private manner on a public blockchain. Okay, so as I said, we're going to be focusing on non-interactive zero knowledge. And so let's talk about what that is. In particular, we're going to be focusing on, again, snarks, which are non-interactive arguments that are short and very fast to verify. So in particular, we're going to be looking at what's called a preprocessing snark. So what's a preprocessing snark? Again, we have a circuit that takes, a statement and a witness and outputs some value in the field. A preprocessing snark is basically a triple of algorithms. Yeah, I'll call them setup, prove, and verify. The setup algorithm is what preprocesses the circuits. Yeah, so the notation I like to use is that when we preprocess the circuit, we output these two setup parameters, one for the prover, SP, and one for the verifier, SV. Okay. Now, the prover runs an algorithm that takes the statement and the witness's input, produces a short proof. When I say short, I mean it has to be at most logarithmic in the size of the circuit. Okay. And then the verifier takes SV and only the statement and the proof and either accepts or rejects. And its running time, it has to be very fast. Its running time, again, can only be logarithmic in the size of the circuit. Of course, it has to be linear in the size of the input because of the size of the statement, because the verifier at least has to be able to read the statement. All right, so that's what's called a preprocessing snark, where we preprocess the circuit, and then the verifier is only given the preprocessed circuit. So I want to, again, emphasize that both the size of the proof and the verifier's running time are logarithmic in the size of the circuit. It's kind of amazing that this is at all possible, but in fact it is, and we're going to see how. As usual, we want this to be complete, a proof of knowledge. It's also interesting, by the way, these systems are quite interesting even if they're not zero knowledge. And so I'll say that zero knowledge is optional, but of course, we'd like to add zero knowledge to these proof systems. And generally, there's a generic conversion that takes many of these proof systems that are not zero knowledge and converts them into something that is zero knowledge by adding appropriate measures of blinding. Okay, so one thing that you might be wondering is why do we need to have this pre-processing step? Why should we pre-process the circuit? So if this was a live talk, I would kind of pause and wait for somebody to answer. But since it isn't, let me just tell you why. Well, the reason we have to pre-process the circuit is you notice the verifier's running time is at most logarithmic in the size of the circuit. So the poor verifier can't even read the circuit. Well, how is it going to verify the proof if it can't even read what the circuit is? And the answer is that this pre-processing step will generate this string SV, which is actually a very short summary of what the circuit actually is. And now the verifier only reads this short summary. So in some sense, this setup procedure, you can think of it as kind of sort of a offline phase that the verifier runs through to pre-process the circuit, and then online it only reads this very, very short summary. So it's very cute, kind of amazing that it's possible that we can summarize a circuit in such a way that the verifier can then verify that C of xw is equal to 0 just from the summary. It doesn't even see what the circuit is. Okay, so it turns out there's multiple types of pre-processing steps, yeah, and so let's walk through what they are. So the simplest one is where the setup algorithm itself is trusted. What this means is that the setup algorithm basically uses randomness that has to be kept secret. Yeah, so it doesn't just, nobody else can run this setup procedure. There's a particular trusted entity to run the setup procedure. And if somehow this trusted entity is compromised and its randomness becomes public, then everything blows up. And in fact, you might be able to prove false statements. And that's obviously quite bad. So this is in some sense not what we'd like, but it turns out we get the most efficient provers in this sort of system. The next step up is to have a trusted setup, but it's a universal setup. So in other words, the setup procedure uses secrets, but they're independent of the secret of the circuit that we're going to be evaluating. So the way to think about this is that the setup procedure is kind of divided into two parts. There's an initialization, and then there's the actual pre-processing. And the initialization doesn't depend on the circuit. It produces this universal string that's a one-time setup. In fact, there are secrets required for generating this U, but it's a one-time setup. And then when we pre-process the circuit, we actually only use U, but we don't need any secret data in order to do the pre-processing. So anyone can verify that the pre-processing was done correctly as long as they believe that initialization was run correctly. And in fact, most of these systems also have this property called updatability, which means that anyone can come in and re-randomize U, such that if anyone who's ever re-randomized U is honest, this U will be valid. Yeah, so this is kind of the next step up. And the best we can do, of course, is build a transparent system where the setup procedure doesn't use any secret data. Anyone can verify that the setup was actually done correctly. So, we'd like to get to transparent systems, but the less power you give the setup procedure, the more complicated the proof system becomes. Yeah, that's kind of where we are. Now, there's been a ton of work on proof systems, as you know. I'm going to go through this very quickly because I want to get to the actually heart of the talk. So already Kilian and Mikhaly showed that the PCP theorem implies these succinct transparent arguments. Unfortunately, the prover time was not linear, and so this is somewhat impractical to use in practice. There was a big breakthrough in 2013. The GGPR results show that we can actually have linear time provers or quasi-linear time provers with constant size proofs and fast verifiers. These initial round of results actually required a trusted setup per secret. Yeah. So again, the setup algorithm uses secret randomness that's unique to every circuit. So if the setup is compromised, everything sort of blows up. But then, fortunately, there's been more work since then. We can actually, T-Systems, Sonic, Marlin, Planck support universal trusted setup. And in fact, now we even have systems like Dark, Halo, Stark that require no trusted setup at all. Yeah, but of course, Groth16 is still the most widely used system, produces the shortest proofs. It's actually a very efficient prover. And so, but it does require this trusted setup. Marlin and Planck are actually getting quite a bit of use these days. Thanks to the universal setup property that's also updatable. And of course, Starks are supported quite widely as well. So just to kind of quick table to kind of compare these, you can see the Groth16 basically has constant size proof, a linear size. What the data that the prover needs is linear size in the size of the circuit. The verifier runs in constant time. And as we said, you need trusted setup per circuit. Plonk and Marlin are kind of the same, but they have universal setup. Bulletproofs is interesting. Bulletproofs actually requires no trusted setup. And in fact, the only assumption that's needed for the bulletproof system is simply the discrete log is hard. There's no pairing requirements or anything like that. Produces short proofs, has a very short string for the prover. However, the verifier's time actually is linear in the size of the circuit. Yeah, that's the downside. And then Stark and Dark kind of achieve the best of all worlds. Although there are some big O's. The big O is hiding some constants as well as certain assumptions. So this is a very quick summary of kind of where we are. There are many other proof systems out there that are not on this slide. Apologies if I didn't mention your favorite proof system. There's a lot. This is a very active area. There are new proof systems coming up all the time. Lattice-based proof systems and so on are kind of a recent trend. So there's huge amounts of work left to do here. So just to quickly wrap the introduction part of the talk, let me just remind you the way that the Snarks system work is basically somebody writes a program in a high-level language, what's called a DSL, a domain-specific language for Snarks. Yeah, so there are all these languages that have been defined. There are even variants of Python that let you write Snark programs. This then gets compiled into a Snark-friendly format, like an arithmetic circuits or other formats, R1CS, AIR, Plonk with custom gates. These are various formats that a Snark proof system can ingest. So there's a compiler that does this compilation. Then there's a Snark backend that takes the statement and the witness and produces the proof. There's a verification procedure that will take the proof and the statement and say accept or reject. And as I said, generating these proofs generally is actually quite expensive. And as I said, there's a setup procedure that generates SP and SV and gives them to the prover and the verifier. Okay, so this is basically what I wanted to say about just introducing what Snarks are. Now I want to kind of switch gears and be a bit more technical and kind of talk about how to build a Snark. Now, I wish I could just describe kind of the entire inner workings of a Snark, but I tried, and I think it's very difficult to describe a Snark from beginning to end in one lecture. So what I'll do is I'll kind of give you the high-level ideas for the different building blocks, and we'll see some interesting techniques that come into play. So generally, Snarks are built from two ingredients. Yeah, there's what we call a functional commitment scheme. And again, we'll see examples in just a minute. And functional commitment schemes are cryptographic objects. They're based on complexity assumptions. And then there are these things called interactive oracle proofs. These are information theoretic objects. When you put them together, you end up with a Snark for general circuits. As I said, generally, these Snarks are interesting even if they're not zero knowledge, although typically you can apply a generic transformation and transform them into a zero knowledge Snark. Yeah, there's a general way to lift a Snark into a ZK Snark just by adding some more blinding. So I think for the rest of the talk, I'm going to focus on the Snark aspect and not so much on the ZK aspect, because that's kind of where most of the action is. So we have these two ingredients, functional commitments and IOPs. So let's start with functional commitments. So what is a functional commitment? So I'm going to define, so we have a family of functions from f to the n to f. I'll call this capital F is our family of functions. I'm going to define what we call a function hiding functional commitment. So what is a function hiding functional commitment? It's kind of a cute object. Basically, there's some public parameters that are generated. Now we can commit to arbitrary functions in our family. Yeah, so R is just a random commitment, random commitment nonce. So we can commit to a description of a function in our family. This bracket F means a description of F. And we obtain a commitment, and we're going to assume that this is a binding and hiding commitment scheme. Later on, so we're committing to a function. Later on, somebody can give us an X and a Y. Somebody can give the prover an X and a Y, and the prover can prove that f of X is equal to Y. Okay, so we're committing to a function. And later on, we can open the function at only one specific point, X, to prove that f of X is equal to Y. And the verifier looks at this proof. The verifier is given X and Y. looks at the proof. Of course, the verifier is also given the commitment and says, yes, f of x, the committed function satisfies f of x is equal to y, or no, it does not satisfy it. And the requirements you can sort of imagine, I'll just write them very briefly here. Basically, soundness means that if the committed function is not in the family, or f of x is not equal to y, the verifier should reject the proof. As usual, we want to say that this is an argument of knowledge for the function f. So there's an extractor that will extract f from the prover, from an honest prover, from a prover that successfully convinces the verifier. As I said, optionally, we might want this also to be a zero knowledge proof. And then, of course, we want this to be succinct. So we're looking for a short proof where that's actually easy to verify. So the verifier should run, again, in logarithmic time in the description of the function. Okay, so that's called a functional commitment scheme. Yeah, it's kind of an interesting concept. You commit to a function, and later you can open the function at any point you like. We just recently put a paper on ePrint to show how to construct functional commitment schemes for arbitrary arithmetic circuits, polynomial size arithmetic circuits. It basically, this result basically shows that committing to polynomials, so functional commitments for univariate polynomials are complete in the sense that once you build a functional commitment for univariate polynomials, you get a functional commitment for all arithmetic circuits. And it turns out actually the hardest part of doing that is actually proving that the function is well formed, that the committed function really is a function in the family that you want. I also want to mention that there's a dual notion of functional commitments, which is where you commit to the input. These are called input hiding functional commitments. And then later on, you can open the input in any public function. Okay, so later on, so you commit to an input x, and later on for a public function f, you can prove that f of the committed x is equal to y. Yeah, so this is a dual notion. But the thing that's useful for snarks is actually function hiding functional commitments, like I defined here. Okay, so that's a general notion of function hiding functional commitments. And then there are a couple of important classes of function families we need to focus on. So the first example are polynomial commitments, right, where the function family is restricted to be polynomials of a certain shape. So for example, in the case of univariate polynomials, we would like to commit to polynomials whose degree is less than some bound b. All right, so again, to remind you, we can commit to a polynomial in this family, and later on, we want to convince the verifier that the polynomial evaluates to y at a particular point x. Or alternatively, we can commit to a multilinear polynomial in n variables. Okay, so we commit to this multilinear polynomial, and later we should be able to open it at one particular input. Yeah, so if you're wondering what a multilinear polynomial is, it's basically a polynomial where the degree of every variable is at most 1. Yeah, and here's an example of a multilinear polynomial. So that's kind of one category of functional commitments where we commit just to polynomials. More generally, you can imagine committing to linear functions, right? So the function here, the function family here is a bunch of vectors, and the function is defined as the inner product of a vector f and a vector x. We'd like to commit to a vector f, and later on for any x, we'd like to be able to prove that the inner product is what it's claimed to be. And there's even a more general family called inner product commitments, where we commit to vectors u and v, commit to vectors u and v, and later on we can prove that the inner product of alpha u plus beta and gamma v plus delta is equal to a particular value. Okay, so these two, for example, linear commitments are used in the hierarch system. Inner product commitments are used in the they're kind of the heart of the bulletproof systems. There's a lot to say about linear commitments and inner product commitments. Here, all I'll say is that, in fact, it's easy to see that linear commitments imply polynomial commitments. And in fact, inner product commitments imply linear commitments. So there's sort of 3 is more powerful than 2 is more powerful than 1. But in this talk, we're only going to focus on polynomial commitments and the snarks that come from them. Okay, so as I said, there are snarks that come from other functional commitments, but those snarks have different properties, and I'm not going to talk about those today. I'm only going to focus on snarks that come from polynomial commitments. So again, polynomial commitments, we either commit to a univariate or a multilinear polynomial. So basically what we're going to do is take a polynomial commitment scheme where we can commit to a polynomial and later open the polynomial at any input of our choice. And we're going to take what's called a polynomial interactive oracle proof. We'll see what that is in just a minute. It's called a poly-IOP, and we're going to derive ZK snarks for general circuits from these two components. So I have to explain what both of these components are. So let's start with the first component. So polynomial commitment schemes. So the first question you should be asking is, I told you that there are two families of polynomial commitment schemes. One is for univariate polynomials of bounded degree, and the other is for multilinear polynomials with a bounded number of variables. So which one should we be using, univariate or multilinear? It turns out that actually there's very strong parallels between univariate and multilinear. It's like almost anything you can do with one, you can do with the other. But the first observation I want to make is that, in fact, if you have a way to commit to multilinear polynomials, that also gives you a way to commit to univariate polynomials. Yeah, and the way this works is as follows. So suppose we have a polynomial of degree 2 to the n. Yeah, so the degree bound on the polynomial is going to be 2 to the n. Think of n as like, maybe 20. So we're going to be committing to polynomials of degree 1 million, up to 1 million, if n is 20. So if you want to commit to a polynomial of degree 1 million, univariate polynomial of degree 1 million, what we can instead do is commit to a multilinear polynomial that I wrote over here. It's defined over here. So we use the same coefficients as, so the coefficient of x to the I is going to be ai, just like in the univariate polynomial. And the multinomial is going to be y to the binary representation of I. And just to give you an example, y to the binary representation of 5 is y to the 101. 101 is 5 in binary, which means the variable y0 times y2, right? So this defines one monomial in our multilinear polynomial. Okay, so we're going to commit to the multilinear polynomial g. And later on, if we want to open our univariate polynomial, oh, I forgot to say, we're committing to a polynomial of degree 2 to the n, and we need n variables in our multilinear polynomial to do that. Yeah, so always the number of variables into multilinear polynomial is going to be a log of the degree of the univariate polynomial. So later, if we want to open the univariate at a point x, all we do is we open our multilinear polynomial at this point, x squared, x to the 4th, x to the 8th, up until x to the 2 to the n minus 1. Yeah, and you can see that in fact this will give us will give us the correct evaluation of the univariate polynomial. So if I have a way to commit to a multilinear polynomial of n variables, I have a way to commit to univariate polynomial of degree 2 to the n. So why do we care about univariate commitments if we can build them for multilinear commitments? And the answer is that direct univariate commitments tend to be more efficient. Yeah, even though it's a more specialized type of commitment, we can build more efficient commitments for univariate polynomials. So that's kind of interesting. Generally, by the way, the more general the function class is, the harder it is to commit to functions in this function class. Yeah, here we see that multilinear are more general than univariate. And in fact, it's harder to commit to multilinear than it is to commit to a univariate. Basically, that's kind of what this is saying. So let's look at an easy application of these polynomial commitments. Let's look at this thing called a vector commitment. So what is a vector commitment? Here, I want to commit to a vector of dimension d, v0 to vd minus 1. So I commit to an entire vector. And later, I want to open the vector at a particular point. So I want to prove to you that vi, that the ith position in the vector is equal to vi. All right, if you like, you can think about this as sort of committing to the truth table of a function. F of 0 is v0, f of 1 is v1, and so on and so forth. So I'm committing to the truth table of a function. And later on, I want to open this function at one particular I, input I. Well, so it turns out we can do this quite easily using either univariate or multilinear polynomials. What we're going to do is we're going to use points at the domain to encode elements in the vector. Okay, so in the case of a univariate polynomial, we're going to use a cyclic group. Okay, so omega generates a cyclic group of degree d. Yeah, so omega to the d is equal to 1, and it generates this group of order d in our finite field. And in the multilinear case, we're going to use the Boolean cube. So here, 0, 1 to the n, where n is log the dimension of the vector, and we're going to assign each value in the vector to one corner of the Boolean cube. And now how do we commit? Well, we're going to interpolate a polynomial f such that f of omega to the I is equal to vi in the univariate case, and f of the binary representation of I is equal to vi in the multilinear case. Again, these are the corners of the Boolean cube, and these are the elements in this cyclic group. Yeah, so we interpolate these polynomials, and it's actually quite easy to interpolate these polynomials, as we'll see in a second. And now when I commit, I just commit to this function f. This is how I commit to my vector. And now if I want to prove that the ith position in the vector is equal to vi, I just prove either that f of omega to the I is equal to vi or f of binary I is equal to vi. Okay, so you can see that if I can commit to polynomials, I can very easily commit to vectors as well. Now, actually, these vector commitments should look familiar to you. They're basically also implemented as Merkle trees, right? A Merkle tree literally gives you a vector commitment. So you should ask, well, why am I bothering with polynomial commitments if we can just use Merkle trees to commit to vectors? And the answer is that using polynomial commitments, we can do a lot more than just Merkle trees. For example, we can aggregate many opening proofs into a single short proof. Yeah, I can open the vector at 1,000 points and aggregate those 1,000 proofs into a very simple single proof. Yeah, whereas with Merkle trees, we're stuck with 1,000 proofs that we have to check one by one. I'll show you how this aggregation works in just a minute. Okay, so the next question then is, how do we construct a polynomial commitment scheme? And it turns out, again, this is a very active area of research. There are lots and lots and lots of constructions. There are constructions that require a trusted setup. The classic one is called KZG, due to Kate et al. Back in 2010. There's an improvement of KZG called inner product pairings, IPP. This is due to Bunz et al. We'll talk about the improvement in just a minute. There are polynomial commitments that don't require setup at all. Things like Dory, Dark, Starks, and so on. That don't require trusted setup at all. What I want to do here is quickly show you abstractly how to build a polynomial commitment scheme, and then I want to focus on applications of these polynomial commitment schemes because they're really quite interesting. Okay, so let's construct a PCS abstractly. All right, so what does it mean to construct it abstractly? What I'm going to do is I'm going to assume that I already have a way to commit to certain functions. Okay, so given a secret alpha, I can commit to a function f and obtain a commitment m. The commitment scheme is only going to be binding. Yeah, it's not going to be a hiding commitment because we're not focused on zero knowledge. We're only focused on soundness or proof of knowledge. So we're going to have a binding commitment to this function f, and this could be either for univariates or multivariates. And I want a binding commitment to satisfy two properties. The first property is I want it to be linear. So in other words, if I take the commitment, I can so given a commitment, I can multiply it by b and add it to another commitment, and I'll get the commitment to the polynomial b times f plus g. Okay, so the commitment scheme is a linear commitment scheme. The second property I want is that it supports what we call product tests, which means that if I give you a commitment to f, g, and h, you can test if f is equal to g times h. And anyone can do this test. Yeah, just given the commitments, you can test that f is equal to g times h. Clearly, this means these commitment schemes are not hiding; they're only binding. And the way these product tests work, I'll tell you, this is basically where pairings are needed. So because I don't want to talk about pairings, I'm just going to abstract it away, and I'm just going to assume we have a product test available to us for this commitment scheme. Yeah. The other thing that's interesting is that to compute a commitment to a function f, I need this secret alpha. And as we'll see, alpha is only going to be known at setup time, and then we're going to throw away alpha. Okay, so this is a trusted setup where during setup time we can commit to a number of polynomials, then alpha gets erased, and then the goal is basically to build a PCS from whatever we constructed. Okay, so let's see how these PCSs work. It's actually kind of cute, and I'm going to do both univariate and multilinear at the same time. What I want to do is kind of show you the duality that really working with univariate polynomials and working with multilinear polynomials is almost the same thing. It's very, very, very close. So in the univariate case, we commit to a polynomial of degree d. In a multilinear case, we commit to a multilinear with n variables, whereas always d is equal to 2 to the n. Okay, d is equal to 2 to the n. All right, so how do we commit? Well, you remember that for univariates, we have Lagrange interpolation. We know that we can evaluate the polynomial at the subgroup. We can multiply by these Lagrange polynomials. Here, I wrote down the Lagrange polynomial here, and we'll interpolate the polynomial f of x back. Now, by the way, it's interesting. The reason we like to work with cyclic subgroups is, okay, at least one reason we like to do it. Well, the primary reason we like cyclic subgroups is because then we have an FFT algorithm, fast Fourier transform. But another benefit of working with cyclic subgroups is it turns out Lagrange polynomials become very, very simple to evaluate. In fact, the Lagrange polynomial, when you instantiate it with roots of unity, become this very simple expression here, which you can see is very fast to evaluate. So we can evaluate all d Lagrange values basically in time, in linear time in d. This is an important thing to remember. If I give you the points of a function evaluated at a cyclic subgroup, and you want to evaluate the function somewhere else, then it turns out you can do that in linear time just by evaluating these Lagrange coefficients very, very quickly. So this is kind of a quick, cute trick to remember that Lagrange polynomials on cyclic subgroups are actually quite simple polynomials. Well, it turns out we have a very similar interpolation formula also on the multilinear side, right? We can basically write f of x as a sum of the values of the multilinear function evaluated on the Boolean cube, right? Bin I, the binary representation of I. These are the corners of the Boolean cube. So we can evaluate it given its value on the Boolean cube times something that plays the role of Lagrange polynomial. These are called these equality functions, and I wrote down what the equality functions are for you down here. You can convince yourself later on that in fact this is a correct way to interpolate a multilinear polynomial. Okay, so either way we have a nice interpolation formula, and what this means is that actually at setup time we can commit on the univariate side. We can commit to all the Lagrange polynomials, L0 to LD minus 1. On the multilinear side, we can commit to all the equality functions that correspond to all the points in the Boolean cube. Okay, so we have 2 to the n, d equals 2 to the n size parameters on the left, and d equals 2 to the n parameters on the right. And now when we want to commit to a function f, all we have to do is just look at the values of the function f on the group and use the linearity property of the commitment scheme to compute from the commitments of the Lagrange polynomials, compute a commitment to the function f. And similarly here, from the commitment to the equality polynomials, compute a commitment to the function f. You see, it's almost the same. Univariate and multilinear, basically these commitment schemes work almost the same. What's interesting is we get basically a constant size commitment, and we can compute these commitments in linear time. Yeah, given the evaluations of the polynomial, all we have to do is just do this simple inner product, and we get the commitment to the function f. Okay, that's how we commit to a polynomial. The next question is, how do we open the polynomial? So now we want to prove that f of u is equal to v, or f of a vector u is equal to v. So how do we do that? Well, here it's kind of interesting. So again, I want to do the duality. I want to show you the duality between univariate and multilinear. So I'm going to do this slightly abstractly, but I hope this will be clear. So let's look at the polynomial f minus v. So what do we know about the polynomial f minus v? Well, f minus v happens to evaluate to 0 at the point u, if the statement is correct. Yeah, this will evaluate to 0 at the point u. So what we'd like to do is prove that the polynomial f minus v belongs to the ideal of all polynomials that happen to evaluate to 0 at the point u. Yeah, so we look at the set of all univariate polynomials of degree d, actually all univariate polynomials that evaluate to 0 at the point u. That set is an ideal, and the ideal is generated by the polynomial x minus u. Yeah, so any polynomial in this ideal must be a multiple of the polynomial x minus u. Okay, that's what this means. And so what does it mean that f minus v is in this ideal? Well, what it means is that there's a quotient polynomial such that f minus v is equal to q times x minus u. Again, this might seem a little bit of a strange way to derive the fact that there's this quotient polynomial, but it's going to make sense when we go to the multilinear case. Okay, so we know that there's this quotient polynomial that satisfies this equation. So all we're going to do to prove that that f of u is equal to v is we're going to commit to the quotient polynomial q. And now we're going to use our product test to test that a commitment to the quotient q times x minus u is equal to f minus v. Okay, so that's basically where we use our product test. And if this is true, it means that this equation holds. If this equation holds, f minus v is in the ideal, and that proves that f of u is equal to v. All right, so that's basically how we prove that f of u is equal to v. By the way, this basically security of this reduces to security of the underlying commitment scheme. And proving security that the underlying commitment scheme is in fact binding, unfortunately, that requires non-refutable assumptions. So I won't state those here. Just know that that actually requires fairly strong assumptions to prove that this type of system is secure. Okay, so this is how we prove that f is equal to u, fu is equal to v on the univariate side. On the multilinear side, it's really the same thing, except using multivariate polynomials. So again, we want to prove that f minus v is in the ideal of all multivariate polynomials that happen to be 0 at u. Right? That's what we're trying to prove. This ideal happens to be generated by n polynomials, these n linear polynomials. What that means, again, is that there exists n quotients, such that f minus v can be written as a sum of these n quotients. All right? That's actually why using these ideals is useful, because it generalizes quite easily to the language of multivariates as well. And so the way the proof that f of u is equal to v is going to be a commitment to these n quotients. And again, we use the product test to verify that this equality holds, that really that the equality that I have over here really holds given only commitments to the quotients, commitments to the linear polynomials, and commitments to f minus v. This we can check using our product tests. All right, so you can see that we can build a polynomial commitment scheme using either univariate or multilinear polynomials. So really, we have these, for univariates, we have a way to commit to polynomials. As I said, the public parameters are of size d. The commitment is constant size. The proof is constant size. Verifying the commitment computing the commitment takes linear time. Computing the proof, computing this quotient takes linear time, but verifying the proof takes constant time. This is, again, quite remarkable that we can verify in constant time. For multilinear polynomials, the proofs are going to be longer. They're linear in the number of variables, and verifying the proof is also linear in the number of variables. It turns out these inner product pairings of Boons et al., what they do is they're kind of the same as commitments in the univariate case, except that the public parameters become shorter. They're square root of the degree. The proof becomes a little bit longer. Verification becomes a little bit longer, but the time to generate a proof is substantially shorter. Okay, so we save on the public parameters and the prover's time, paying a small cost for verification and proof size. And finally, Dory does the same thing. Dory is a very beautiful polynomial commitment scheme. It does the same thing as inner product pairings, but it's able to avoid a trusted setup. Okay, so we have lots of examples of interesting polynomial commitment schemes. Again, these are, I kind of linked to these papers in the PDF. These are really beautiful ideas that I kind of highly recommend reading. Now, the last thing, that's our polynomial commitment schemes. So now we understand how PCSs work. The next question is basically how to use them. And the way we use them is by actually introducing these polynomial IOPs. And so let's go over what polynomial IOPs are. Okay, so a polynomial IOP is basically, it's called an interactive oracle proof. Again, the goal is to prove that a circuit is evaluates to 0 at x and w. And so again, we're going to have a setup procedure where the setup procedure basically commits to a bunch of polynomials. Yeah, so I'm thinking of these as polynomials in a box. So we send to the verifier sort of a commitment to a number of polynomials. We do that during setup phase. This is a summary of the circuit C. Now, the prover, what it will do is it will send the polynomial to the verifier. The verifier will send some randomness. They'll do this over and over and over again. And eventually, the verifier has a verify procedure that will query the polynomials at a bunch of points. It's also given the randomness that the verifier chose. But the main point is it can evaluate these polynomials at any point that it wants, and then it decides whether to accept or reject. So we think of these as sort of information theoretic objects because security here, the properties are supposed to be the usual properties, and security here is basically completely information theoretic, assuming that these polynomials are given, the verifier only has oracle access to these polynomials. So the polynomials are not actually sent to the verifier. They're kind of sent in a box to the verifier, and the verifier only has oracle access into these polynomials. Okay, so that's what an IOP is. And of course, you can build a Snark from it in kind of the obvious way. Basically, you're going to replace the boxes by polynomial commitments. You're going to use Viet-Shamir to make the system non-interactive. Then it turns out here, I'm going to go very quickly over this. I just wrote down what the proof size is, what the verifier time is, and what the prover time is. Directly, you can kind of read the proof size and running times directly from how the IOP works. Okay, so the IOP actually translates to a Snark by plugging in a polynomial commitment for all the boxes. All right, so now this is kind of where the fun begins. Unfortunately, almost towards the end of my talk is where kind of the interesting things are. So please pay attention. I'll try to do this in 5 minutes, and then we'll leave 5 minutes for questions. So the question is basically, what are the how do we use how do we construct a polynomial IOP for arbitrary arithmetic circuits? And so there are a couple of building blocks to do that. The building blocks basically are kind of interesting IOPs for interesting statements. So I want to show you kind of 3 interesting statements that we'd like to prove, and all the Snarks out there basically use 1 or 2 or 3 of these statements. So again, we're going to focus on the univariate case. So imagine we have a cyclic subgroup of order k, and we have some polynomial f whose degree is bigger than k. Yeah, so maybe its degree is 2k or 3k. The things we'd like to prove about this polynomial, so the polynomial is committed to the verifier. So the verifier has the polynomial in a box. It can only have oracle access to this polynomial. And we'd like to minimize the number of queries into the polynomial. And yet we'd like to prove one of 3 things. The first thing we'd like to prove is what we call a 0 test. That say, prove to me that f is in fact identically 0 on the subgroup. So it doesn't have to be identically 0 on the entire field. It just has to be 0 on the subgroup. How do we do that? The second task is what's called a sum check. Prove to me that the sum of all the elements over the subgroup is equal to some value b. And the third task is what's called a product check. Prove to me that the product over all the elements in the subgroup is equal to some value c. Okay, so these are 3 standard tasks that we'd like to use. It turns out Marlin uses a sum check and Planck uses a product check. Yeah, so these are kind of the fundamental blocks that go into these polynomial IOPs, Marlin and Planck. Now, you can ask exactly the same questions about multivariates, right? So for a multivariate, we have the Boolean cube. We'd like to do a 0 test on the Boolean cube. This is supposed to be Bn. We'd like to do a sum check on the Boolean cube or a product check on the Boolean cube. Well, so a sum check is sort of the classic sum check protocol from the 90s that I'm not going to describe here. I mean, this is a classic protocol for doing sum check that the sum of elements over the Boolean cube is equal to a particular value. It turns out a 0 check directly follows from a sum check. This is kind of a cute homework problem. You know, if you have some time to think about this, try to derive a 0 test from a sum check. It's not that difficult. And then a more interesting homework problem is try to derive a product check from multilinear polynomials. Yeah. So again, it turns out this reduces to a sum check. You can do it. If you have an interesting solution, please send it to me. I'd be curious to look at your protocols. You can do it using a number of sum checks. You know, I kind of have a way to do it, but I'd be curious to see if you have other interesting ways of doing this product check. Okay, so as I said, these 3 tasks are sort of at the heart of Planck and Merlin. So let me show you how to do, maybe I'll just show you how to do the 0 test, and then unfortunately, I think we'll stop and take some questions. So let's look at a 0 test and some generalizations. So how do we prove that a polynomial is 0 on the entire subgroup? Well, so if the polynomial is 0 on the subgroup, we know that it has to be divisible by the polynomial x to the k minus 1, because the polynomial x to the k minus 1 is 0 on every element in the subgroup, right? So again, we have a subgroup of order k. So therefore, the polynomial x to the k minus 1 must be 0 for every element in the subgroup. And since f is 0 for every element in the subgroup, it must be the case that f is divisible by x to the k minus 1. Okay, so that's going to be our quotient q. And then what we'll do is we'll send the commitment to the quotient Q. I forgot to say, by the way, the verifier only has a commitment to the polynomial f. We'll send the commitment to the quotient Q. And now what the verifier prover will do is they'll run through the opening protocol. The verifier will choose a random point R. They'll run through the opening protocol to evaluate Q of R and F of R. So the verifier learns Q of R and F of R. And now the verifier can just check that F of R is equal to Q of R times R to the K minus 1. Right? So we basically check this identity at a random point. And as you know, if this identity happens to hold at a random point where the field is sufficiently large, this implies that, in fact, these two polynomials are equal. This is assuming the field is sufficiently large, much larger than the degree of the polynomial. Okay, so yeah, so as long as d over f is negligible, this is a complete and sound protocol. What's interesting thing here is the verifier's time is logarithmic, log k, because it has to compute r to the k. It only requires 2 evaluations. Yeah, just 2 evaluations of a protocol. We can prove that a polynomial is 0 everywhere. What's interesting is this generalizes actually to do what we call batch opening. Okay, so suppose I want to prove to you that f of ui is equal to vi at a bunch of points, let's say at 1,000 different points. So this is relevant to our vector commitment construction that we saw earlier. If I want to prove to you that the 1,000 vector openings, it turns out I can do it using a single opening of a certain polynomial f, which is again much better than a Merkle tree, right? I only need to do one opening of a polynomial, as we'll see in a second, and that will prove to me that the vector commitment is a certain value at 1,000 different positions. So let's see how we do this. So the verifier, what it will do is, first of all, it will interpolate a polynomial that maps ui to vi for all I to s. Yeah, so this is a polynomial of degree s minus 1. This is the s polynomial. It will also compute the polynomial z of x, which happens to vanish at all the u's, at all the point u's. Okay, so this takes the verifier linear time in s to do. So it's linear work for the verifier, linear work in s, but that's okay. The prover is going to do the same. It's going to compute s and z, and it's also going to compute a quotient polynomial, which is s minus s divided by z. Again, if in fact f has the correct value, f satisfies this relation, then in fact f minus s will be 0 at all of u1 to us, and therefore this polynomial f minus s will be divisible by z. The prover will send q over to the verifier. The verifier now will do the same. They'll open q and f at one random point r, and then verify that f of r is equal to qr times zr plus s of r. That's it. Yeah, that's the whole proof. And now we've basically proved that the polynomial f is equal, that f of ui is equal to vi at s different points. So we get a constant size proof. You notice it's only 2 openings. So it's a constant size proof that the vector evaluates to s different values, the correct values at s different points. This is much better than what we would get with a Merkle tree. So I would have loved to tell you more about polynomial IOPs. In fact, I wanted to show you how to do a product check, but unfortunately, I think we're running very low on time. And so what I'll do is I'll jump. I'm happy to make these slides available. If anybody wants the slides, feel free to email me and I'll send you the slides. I'm also not going to be able to describe Plonk. So let me just jump to my final thoughts. In that there are, in fact, many, many ways to compare ZK snarks based on proof size, prover time, verifier time, whether it's transparent or not, is it quantum resistant or not. And the amazing thing is there's no single snark today that dominates over all others. Yeah, maybe we'll have one in the future, but today, depending on which things you want to optimize, we get different types of snarks. One thing that I wanted to mention is that there's kind of a recent interesting comparison criteria, which is what we call collaboration friendliness. And I'll just say that the question is basically, what happens if the witness itself is split across many provers? So it's not a single prover that holds the witness, but you have, in fact, many witnesses, many provers that each hold a different part of the witness, and they'd like to generate a proof without revealing the witnesses to each other. So what we'd like to do for that is use a snark that's actually MPC friendly. We'd like to use to run the prover's algorithm as an MPC. And the question then is, which Snark should we use if we want the prover to be MPC friendly? And it turns out, again, Gros 16 actually is the most MPC friendly. Marlin is second most, Planck is third, and Stark is a little hard because it uses a lot of hash functions. And so it's interesting. There's even another criteria that people try that we can compare Snarks with, and we'd also like to make them. We'd like to make the prover's algorithm as MPC friendly as possible. I think this is still there's a lot of work to do in this area. Coming up with Snarks that are as MPC friendly as possible would be a wonderful area for future work. Okay, so as I said, this is very exciting times in the world of ZK Snarks and polynomial commitments. There are lots and lots of beautiful ideas, and I'm sure there are many, many more coming. Hopefully, many more ideas coming from you. And so I'll stop here. I went a little bit over than what I anticipated, but if there's time, I'm very happy to take any questions. So thank you very much.
Thank you very much, Dan, for this talk. It's actually really hard to compress all this, as you said, this booming area in a talk. So I think this high-level description is highly appreciated. So we have one question from the audience. I also have a couple of, so I think we would go for 10 minutes if you're okay with it, because I think there's so much to talk. No, so I see another question here. Okay. So first one is about the workings of IOP. So I think it's how are IOP implemented? Who holds the polynomial in the box?
Yeah, that's actually a really, really good question. Thank you for asking, Elena. So the idea is that, in fact, IOPs are kind of these abstract concepts where the polynomial does sit in a box and it's not clear where the box is. But in reality, the way it's implemented is using commitments, right? So really, IOPs are just a way to talk about proofs without having to talk about polynomial commitments, right? So the polynomial is actually committed to the verifier. The verifier is holding a commitment to the polynomial, and then using the opening protocol for the PCS, the verifier can query the polynomial at any points of its choice, but it doesn't learn anything else about the polynomial. Yeah, so the way it's implemented, as I said, is using commitments, and that gives the verifier oracle access to the polynomial and nothing else. So yeah, thanks for asking. It's a good question.
So there's another question by Danielle, who asks, could you please give some more details on some standard techniques to achieve zero knowledge from a non-zero knowledge proof?
Oh yeah, that's another excellent question. Thank you, Danielle. Right. So usually what happens is if we have a linear polynomial commitment scheme, so it satisfies the linearity property that I showed you before, it turns out you can sort of apply a sigma protocol to lift it up into zero knowledge, right? So initially you commit to a random polynomial, the verifier then sends a challenge, and then you commit to sort of the challenge times the real polynomial plus the random polynomial, like we do in Schnorr style proofs. Yeah. So generally, I mean, it takes a little bit more work in the area of Snarks to show that this works, but generally, this sort of blinding technique makes this into a zero knowledge opening protocol. You also need to make sure that the commitment itself is hiding, and it turns out you can make the commitment hiding basically by adding a few dummy points to the polynomial. You require the polynomial to evaluate to some random values at a couple of evaluation points, and it turns out that makes the commitment into a hiding commitment. Yeah, so these kind of generic tricks. If your PCS, your polynomial commitment scheme, satisfies some basic properties, these kind of generic tricks that we've seen in other areas will basically make the Snark into a zero knowledge Snark. Yeah, it's a very good question.
I would like to ask something. So I like very much the summary that you make, like this product check, sum check, and the first one.
The zero test. Yeah.
The zero test. Yes. So, and actually, yeah, I see the apps like this is the grand product. No, this product check. I think this is the grand product argument. So I think this is like really what's happening. Like this is what people are using. But my worry was always that I think if you don't work in this area, it's very hard to make a mapping from what really happens in the circuit description, like you're trying to prove linear relations, quadratic relations, and how does this turn into a product check? So I thought that so I really like, because these are the building blocks, but I think that the link is missing. So
Yes.
this is why I like that, thinking of the sum check sort of like as an inner product or things like this.
No, that's actually a very, very good point. In that, I wish I could speak for 2 hours about this, because it's really difficult to. I wanted to go from 0 to snarks in like one talk, and it's very, very difficult to explain everything in a single talk. If folks are interested, I'm happy to share my slides, and the slides actually explain exactly how, for example, the Plonk IOP works. And so what if you think about what Plonk is an example of a snark. What it actually is exactly a way to take a circuit and compress it into 2 polynomials. Yeah, one polynomial represents the gates, and one polynomial represents the wires. Yeah, and you can commit to these 2 polynomials, and that's the summary of the circuit. Yeah, and then later on, you can prove that you have a satisfying assignment to this polynomial, to the circuit. And the whole beauty of Plonk, and actually this is where it needs the product check, is actually to verify that this assignment that you have really is consistent with all the wires and the gates of the polynomial. So it's really very elegant, I have to say. It's very, very pretty. And I'm sorry I couldn't go for another maybe 30 minutes to describe how that works. But that actually, the description is, as I said, is in the slides, and that's all done as a polynomial IOP. So yeah, if you're interested in seeing it, I will point to the slides.
So I would like so I got some other questions from through another chat. So if you like, I don't mind, I will ask you.
Sure.
So one question is, do multivariate polynomial commitments offer any advantage over univariate ones when using them to construct snarks?
Yeah, that's an interesting question. That's right. So in fact there are some poly IOPs that are specifically designed for multilinear polynomials, like Spartan is an example of that. It turns out the most practical ones are using univariates, and that's actually why you see most of the deployed snarks actually use univariates. Primarily the reason is because univariate commitments are shorter than the multilinear commitments. It gets a little tricky to compare, because you could actually ask about the prover's running time, and it turns out the prover's running time is a little different in both cases, but it's very difficult to compare, because in one case you're comparing, perhaps you might be doing more field operations, but in the other case you might be doing more exponentiations. So it becomes very, unfortunately, I can't give a concrete answer, because it becomes sort of, more of one thing versus less of something that's more expensive.
Is there some advantage in terms of computational assumption? Because it's like the
computational assumptions are the same.
Okay.
Yeah, that's kind of interesting. Computational assumptions are the same in both cases.
Okay. So I have a last question, which is most snark starting point is the arithmetic circuit model, which captures non-uniform computation. This is stronger than NP. Is this possibly an overkill, and avoiding it could give more efficient constructions?
Yeah, it's a good question, and it's a fair point, but probably not, right? Because in most cases, the circuit actually, when you say this is non-uniform, it's only non-uniform in the sense that, for large input sizes, maybe the circuit is hard to come by. But in all practical applications, the circuit is actually quite easy to describe. Yeah, so you don't benefit from non-uniformity in any way. And in fact, the circuit is quite concrete. So yeah, so it's not clear that there's any benefit to be had from the fact that it's non-uniform, or moving away to something simpler than the circuit model. I have to say, circuit, by the way, there are many ways of describing the circuits, right? I mentioned R1CS, I mentioned air, I mentioned other methods. There are many ways to describe the circuit. They're all equivalent, And for some of them are better for snarks than others, but those are mainly from a prover efficiency point of view. They're all equivalent to describing arithmetic circuits. And like I said, in all practical applications that I know of, the circuit is actually very concrete and quite explicit. So there's no non-uniformity is not an issue, really.
So this same person asks, do you think that snarks for uniform computations, for example, using Turing machines, is an interesting research direction?
Very, absolutely. Yeah, absolutely. I highly encourage you to do that. The fact that we're bound by a finite input is problematic in some cases, and so yes, if you could do snarks for Turing machines, that would be fantastic. Highly encouraged.
Okay. Well, thank you very much. I also feel like I could keep talking for a long time. So, and we really appreciate your time and that you're here virtually with us in Bogota. And thank you. And
yeah, thank you all. Thank you very much. This was fun, and I hope to be at a next Latin Crypt in person. Thank you all.
We hope so too. Okay, bye.
Bye.
We now have a break. And we will resume at 12:30. Thank you, everyone. Goodbye.